Okay, it's a pleasure to introduce Xavier Gómez-Mont. I mean, he's well known in Mexico and abroad. He works in many different kind of areas, complex geometry, foliation, singularities. He's going to talk about the total Dehn twist of the monodromy of a plane curve singularity using Hodge theoretical invariants.
Okay, I'd like to thank the organizers for giving me the opportunity to speak in this workshop. And also, I am very pleased for this agreement with this Mathematical Institute of the Americas. I think it's a great opportunity for Mexican mathematicians, and as we all know, it's more important to build bridges than to build walls. So this is going to be like a tutorial to Professor Griffith's talk. So if you got lost there, perhaps here you'll find your way. So I'm going to speak of a relation between singularity theory and Hodge theory. And in the case of singularity theory, I'm going to concentrate in the case of plane curve singularities. As you will see, as the thing proceeds, many of the things I will say actually are true in a more general context. But in order to be very concrete and down to earth, I'm going to do it for the case of plane curve singularity. So this means that we're going to have a function f from C2 to C, and a holomorphic function, or we can think it's a polynomial, and is sending 0 to 0, and we're going to look at it in a neighborhood. So we're going to think that partial of f with respect to C0 is equal to partial of f with respect to C1 is equal to 0. So if this hypothesis is not satisfied, we all know from our calculus courses that in the neighborhood of 0, things look like this. That's what the implicit function theorem says, which is a very boring situation. So in the calculus course, this is enough, but we're going to assume that we're at a singular point. Now, Milnor's description of what's happening here is the following. We have in the image, we have the disk. Then above 0, we have a singularity. And then for a value t0 different from 0, we have something which has the same boundary, but it brings out some topology. And in the case of plane curves, so this will be a surface, compact surface, boundary. Now, if the function f can be factorized into irreducible components, into R irreducible components, so this means that f minus 1 of 0 is going to be formed by the R. So we put f1 equal to 0, f2 equal to 0, fr equal to 0, so we have something that looks like this. And so this f minus 1 of t0 is going to look something like this. We have several boundary components, And then we have something like this. And then we have the genus here appearing. So this will be a compact surface with boundary connected. Then Milnor's description asserts that this f minus 1 of T0 is homotopically a bouquet of mu one-dimensional circles, mu, where mu is equal to the dimension of the first cohomology group of V, complex coefficients A, and also it can be characterized as the dimension of O of C20 divided by the ideal generated by the partial derivatives, F0 and F1. So this is, so actually in what I'm going to say is going to be most interesting if there are more than one connected component in the boundary. So we're going to be assuming, to make things more interesting, that these are several irreducible components. And then Professor Griffiths mentioned this, the Holonomic map is the following. So here we take, so we obtain a Holonomic map, which is M of, which goes from this fiber, I'm going to call it F minus 1 of T0. I'm going to call it V of T0. So this goes from V of T0 to V of T0. It's a diffeomorphism, which is the identity on the boundary, of VT0, and it is unique up to isotopy. It means that the map itself is not fixed. What is fixed is the isotopy class of the map. And then, so this map here is called the geometric monodromy. And is an element of what is called the mapping class group. Now, the algebraic monodromy, we do the following thing. We have here the puncture disk, and then instead of putting the fiber, what we put is a vector space. We put H1 of VT0 with complex coefficients, and so this is something which is dimension mu, and then this we do for every T0, T0, T1, and so the union of all these for all T0 in the puncture disk becomes a vector bundle with fibers of dimension mu, which has a flat connection that's called the Gauss-Manning connection. Then when we go around a closed loop, we will get a map which will be, so let's call this the geometric monodromy map. And then we get the algebraic monodromy map, which is a map from H1 of VT0C to H1 of VT0C. And actually, this map is also defined in H1 of VT0 with integer coefficients. So since it's a map induced from this diffeomorphism, So it induces an isomorphism, I'm sorry, here with integer coefficients. But if we think of it as in the complex numbers, then is a matrix, and then this MA can be written as the semisimple part times the unipotent part. So this is concentrating the eigenvalues of the matrix, and this one over here is concentrating the Jordan block structure. So I will be mainly interested in the Jordan block structure. That's the I'm going to center in this. So now lemma. So this VT0 may be decomposed as a union of, let's call it W1 union WS union A1 union S prime. So all of these are going to be compact surfaces with boundary, and there exists an integer n in such a way that the geometric monodromy raised to the n will send omega j, and it will be the identity. Or if I iterate sufficiently many times, in each of these pieces it will be the identity, and then this mn restricted to this ak into ak. So these ak's will be annulus, or to think more pictorially, I will call them tubes. They are two tubes. They are tubes. So the picture is going to. So let me. So for example, if f is equal to x squared minus y cubed times x cubed minus y squared, then this f equal to t0. So this vt0 is going to look like this. Is going to look like this. Is a genus 2. So this has two irreducible components, so we have two components, and then it will have two tubes connecting them, and this n will be 10. So this means that for Hodge theory, one is speaking about the algebraic monodromy. One does not speak about the geometric monodromy. It's only the algebraic monodromy. Here, we're speaking about the geometric monodromy. So, the M, so since it's the identity on the boundary, is sending this component to itself. It's sending this component to itself, but it's doing something. In homology, it's moving the homology here. Now, the denominator, of the monodromy theorem asserts that the eigenvalues of the algebraic monodromy are roots of unity, and that the size of the Jordan blocks, in this case, are bounded by 2. So they are at most blocks of size 2. And in this case, the eigenvalues, so here are the eigenvalues, are of the form they have denominator 10. So there's some number, and then they are divided by 10. So that's why if I iterate 10 times, then I only get eigenvalue 1. But, so in this case, what's going to happen is the following. So if I try to figure out what is the eigenvector corresponding to this eigenvalue, it will be some combination of one homology here, but it might be complicated here. So that's why if I raise it to the 10th power, then it will be the identity. So I raise it to the 10th power, and here's the identity. The M transforms this tube into this tube, and this tube into the other tube. And so if I apply it 10 times, since it's the identity here, I get a map from the tube to the tube, which is the identity on the boundary. Okay? And so the question is, if I take, so here I take this loop, so this is a special loop that comes in here. So we take this special loop. So if we call this gamma, if I do M10 algebraic, or even geometrically, so geometrically to this mg to gamma, I will obtain the gamma plus, and then I obtain, it goes once around here, so let's call this beta 1, and this other beta 2, so I obtain gamma plus beta 1 plus beta 2. So the n, I mean, of course you noticed that in this mixed Hodge structure of the singularity, n is a very important invariant, so this is equal to the logarithm of the unipotent part of the matrix, and in this case, this means the following: is going to be 1 over n, then we're going to put ms mu, and then to the n. So, but ms to the n is the identity, and so we get 1 over n mu to the n. And I'm sorry, no. So this is the identity. I'm sorry. So this is going to be equal to, under this hypothesis I'm putting over there, this is going to be equal to 1 over n, the identity minus mu. So the semi-simple part of the monodromy is going to be, mu, so see, the semi-simple part, I'm going to get rid of it, and here I'm taking, so in this decomposition of m as ms times mu, so this, if I view it over the complex numbers, so here I'll have the eigenvalues, and here I just have the Jordan block structure, so it looks 1, 1, 0, this is a block of size 2, and then here I have another block of size 2, say, and then I have ones. So if I take the identity minus the unipotent part, what I get is a nilpotent matrix. So this nilpotent matrix, N, is the one which gives rise to the weight filtration of the mixed Hodge structure So the question I wanted to understand was the following. Who is responsible for the Jordan blocks the algebraic monodromy. And so I have this so I can view the n either in cohomology or in homology. So I have h1 of mc, or I can put integer coefficients here too. h1 of mc, I have this n, and so I have n squared is equal to 0, and so I have the image of n is contained in the kernel of n, and this is contained in h1, and this is contained in 0. So this is the weight filtration for this case, the weight filtration. So the kernel of n, everything which is in homology in this piece will be in the kernel of n. Everything which is here will be in the kernel of n. This one over here is going to be in the kernel of n. The one which is not going to be in the kernel of n is this one, because it's if I apply the monodromy raised to the 10th power, it gives me the same gamma, but with a Dehn twist over each one of these tubes. And so if I subtract m gamma minus gamma, which is this nilpotent part, it gives me exactly this thing over here. Now, in this story of mixed Hodge structure, there's something which is polarized mixed Hodge structure. So the word polarize means that there is a bilinear form coming from topology. Topology, which actually is going to be coming from coproduct. So coproduct gives me a bilinear form which goes from this VT0, I'm sorry, H1. So if I view it in cohomology, coproduct, so this is H1 of VT0C cross H1 VT0C into C, or I can also put rational coefficients here. Rational coefficients. So, and this is an alternating bilinear form, which means that if I put alpha, beta, and if I change them, this is minus beta alpha. Now, it turns out that since M is a diffeomorphism of the surface, so we will have that M of alpha, the geometric, M geometric, or the algebraic, whatever, of the beta is equal to alpha with beta. So a diffeomorphism leaves invariant the coproduct. And so this implies that the N is an alternating operator with respect to this coproduct. This means that N alpha with beta is equal to minus alpha and beta. And so if I put this operator N like this, which goes from cohomology, cross cohomology into C, is a symmetric bilinear form. It's a symmetric bilinear form. And I can also put here integer coefficients, modulo torsion, and I finish here in integer coefficients modulo torsion. And so this gives me a symmetric bilinear form. Homology with integer coefficients. Or if I want to do it in homology, it will just be the intersection product. And so in mixed Hodge structure, it's important this bilinear form plays a role. This bilinear form is the bilinear form induced in the weight, in the graded, so you take the graded associated to the weight filtration, which means that you take the quotient this by this, this by this, and this by this, and then you induce non-degenerate bilinear forms in these spaces, and this is one of them. So this form here is an invariant of the mixed Hodge structure. And so the result that we have is the following following theorem, that if you take with integer coefficients, if you take the trace of this symmetric bilinear form with integer coefficients, trace of this bilinear form, so but here you have to divide 1 over n. So n is this number which makes this thing be the identity on these components. This is equal to the sum of the Dehn twists. So this is also 1 over n. Dehn twists along basis of a basis around the tubes which give rise to non-zero homology. So this means that these tubes, so you take one of these circles, now it can be, for example, if it turned out that there was only one tube connecting the two, then this one is homologous to 0 because it's the boundary of this piece. So and so this doesn't count. You need to have that this has a non-zero, that its class in homology is non-zero. So this gives a geometric interpretation in the mapping class group of an invariant of the mixed Hodge structure of the singularity. That's how we. Now, I will sketch a proof of this result, and you will see from the sketch that this proof will extend to all dimensions. Then these Hodge theoretic invariants are defined in all dimensions. So what we are lacking in higher dimension is what is the similar to the Dehn twist when we have more dimensions than 2. So let me now bring another aspect, which is the singularization. So, and this is done with blowing ups. So the basic blowing up is in coordinate like this. XY goes into X, XY. And what it does is that lines passing through zero is like polar coordinates in variables. So lines passing through the origin are sent into parallel lines. And so this one over here gets mapped into zero, and this is E, the exceptional divisor. Now, here we have coordinates x1, y1. So if here we have a function f of x1, y1, so this is this blowing up process sigma. So this sigma applied to f on x1, y1, then so we put, every time we see x1, we put x, every time we see y1, we put xy. So in the end, we're going to have a big factor of x, and then here we will have some f1 xy. So this is the multiplicity, so the exceptional divisor, so blowing up does not depend on the function. I just blow up the origin. But if I have a function which is vanishing here, then the composition will have an order of vanishing. And so this means that I will get this exceptional divisor, and I will get another curve here, and then here I have my original curve. If here I had several curves, then each one of these will be lifted to a different curve here, but perhaps some curves will lift to the same point if they have the same tangent cone. So the procedure of the singularization procedure, the singularization process for plane curves produces a graph. Actually, what's called a decorated graph. So we put a point for the first exceptional divisor, and then we put its multiplicity. Then we blow up again. Let's think that we only have one component so that it lifts to a unique point. So we think that now here f is irreducible. And so we get another, an E2, and it has a number M2, M1, M2. And then the process, what it produces is a graph where, and then here I put an arrow. This is the curve when it is non-singular and transverse to the exceptional divisor where it's approaching. Now, let's see. So here, so in the geometric picture, we have this. This is first, second. Here we have a third. So here goes, and here goes, and then here the curve leaves. Here we have this strict transform of the curve. Now, I lift the original function defining the irreducible curve, and so this goes into the disk, and so I take a value T0. So I look at f minus 1, this v of T0. So this v of T0, so f tilde equal to 0 vanish with multiplicity m1 over here. So this means that f equal to T0 will be passing m1 times there. And then here it will be passing m2 times. here M3 times, M4 times, M5 times. It's a finite number of times. Now, when I take a loop, around this point T0, and I have a projection map, and here in the points where they intersect, I have something that I have to explain. So I'm trying to explain where do I get these components. So these components will be the part of the Milnor fiber which intersects a tubular neighborhood of this exceptional divisor except a small disk around the intersection. So in this case I have a projection map, and so the monodromy map is going to be permuting these different these different branches. And since they are finite number for every one of them, after a finite number, I get it to be the identity, the permutation. And so that's where I get this. So those are obtained by taking the a tubular neighborhood of the exceptional divisor and intersecting it with f minus 1 of T0. Now, let me explain more. In this case, so this is in this extreme cases, there are only three cases. One case is I have one point which only connects once, like are like this. I have another one which is when there are two, and then I have the ones on which there are three. Now, in this case, I'm going to have a sphere. All exceptional divisors are always spheres. So here, and then I'm going to delete a disk over here. But this is a disk. The covering of a disk is just a disk. So this means that over these components that I have here, they are only disks. In these parts over here, where I have two, then I have to remove two disks. But then this is an annulus. So any finite covering of an annulus is an annulus. And so over these points, I have disks. Over these points, I have annulus. And over these points, so it's a theorem of the singularization theorem that at most I have in the graph points of valence 3. So in that case, I have 3 points, a sphere minus 3 points. Now, finite coverings of a sphere minus 3 points by Riemann-Hurwitz formula, one can compute what is the genus, the Euler characteristic of the thing above, and so it does have topology. So this picture tells me that the picture to imagine the Milnor fiber looks like this. Looks like this. Here I have, so it looks like this. So here I begin here. This is the deeper part, because this I took more blowing ups. So it goes like this, and then I arrive here, and so I have here some topology. And then this over here means that here I have some disks coming out. So this is going to give no topology. But then this other one means that I'll have some tubes coming out. And here I have another topology. Then of this, I have some further tubes coming out. And the monodromy map will be an automorphism here. This perhaps is going to be permuting this, but after a finite number of times, it's going to be the identity. And then so where do these Dehn twists appear? So the theorem is the following. Okay, so this was when I had only one component. It is a theorem of Ledung-Trang that in the case that there is only one irreducible component, then the monodromy is semi-simple. There is no unipotent part. N is equal to 0 for the case of irreducible plane curve singularities. Okay? Now, what happens if I have more than one irreducible curve? So I start doing my process of blowing up. And so I start drawing the graph. E0, E1, here E2, E3. And here, say, I have at this point, I have 2 branches coming out. But then, when I apply the blowing up over here, then they separate. So here I put something like this. Because see, at this point, the 2 branches separated. And so, and then I continue each branch as if it was an irreducible branch. And here it goes out. And here I have this one. So this is the curve C1 tilde, and this is the curve C2 tilde. And so I get, so if I only take one of these process, is a graph for the irreducible. This one is a graph for this irreducible one, but they have some common part. So how do I know that from these, which are the ones, so which are the gammas which produce the Jordan blocks? So these points where there are valency 3 or more, well, for example, this one has more valency, these are called rupture points. So, fix a path between 2 consecutive rupture points. So in this case, it would be something like this. No? So we have this one and this one. So we would choose this path over here. Now, if the tubes corresponding to this path contains more than one tube, then it gives rise to a Jordan block. So this means that we will be having, so the thing comes in like this, it's coming in like this, and here we have a piece which perhaps has some topology, which is uniting several of these piece over here. So I have the piece over here, I have the piece over here, and I'm just looking at this part. So if I can find, so this means that I go through one, and then I come to the other. So in terms of the graph, it corresponds to having paths which are connecting rupture points. So I'm sorry, rupture points means that, so it would be, no, not this one. This is not a rupture point. This would be a rupture point. It only has 2. And so, now, so that's a geometric interpretation of the trace of this bilinear form, and this locates where the loops which carry the non-trivial monodromy. Now, there is another invariant that we would like to compute 2, which is the following. See, here I said in this is Dehn twist along bases around the tubes which give rise to non-zero homology. And so we have a bigger sum, which is when it doesn't matter if it gives rise to non-zero homology or not. So this one over here is the total Dehn twist of non-trivial topological loops. And then we have another total Dehn twist where we sum whether or not the tubes give rise to trivial topological loops or not. So this is a bigger, all these numbers are positive. They're all positive. There is no cancellations. And so we also have this number. And so we are looking for the following, so we have the following conjecture that we're trying to work on. All this is work in common with Alanis, Cal, Bonatti, González Villa, and we have the following conjecture is the following. So I observe that, so we have O of C2 divided by the partial derivatives. So this is the Jacobian algebra of F. This has a bilinear form, which is given by Grothendieck duality, which is the following. You take GH, and then you send it 1 over 2 pi I square integral, and here you put F1 equal to F2 equal to epsilon, and here you put GH times F1, F2, DC1, DC2. So this is called Grothendieck duality. It's a non-degenerate pairing. It's contained in, and I first learned it from Philip's book. It caused me a great impression what this meant. And so you have this is a non-degenerate pairing. And it turns out that using the mixed Hodge structure, one can relate this Grothendieck bilinear form to the coproduct that I explained over here. And so here we're going to do the following. We're going to have Grothendieck pairing, but we're going to put multiplication by F. As we did over here that we put the N, we're going to put the F. There's a theorem of Varshenko that says that multiplication by F, when you take the grading associated to a certain flag, is the N, And so this one is equal to, so it's the N plus, then there is another bilinear form over here, which, so this has topological meaning, and this has geometrical meaning. So this means that if we move F in an equisingularity class, this part is fixed by the topology, but this part can move. And so we're trying to interpret this total Dehn twist as the real part of this Grothendieck bilinear form when we put here multiplication by F. So, but this is, we just, in some examples we have computed it works. For example, for quasi-homogeneous and semi-quasi-homogeneous singularities, but we don't have a proof of this. So here the condition is that F has an isolated singularity. Yeah, so the conjecture is that the trace, so the trace of this form, so the trace, so it's similar as this one. So the trace of this form So the trace of this form, here I'm putting the n, so this n is equal to the logarithm of the unipotent part, which already it contains the information of 1 over n of raising to a power and then getting rid to the semi-simple part. So in here I don't have to divide by n. If I take n to be this, then this gives me this formula. And so this takes part of the Dehn twist in the part which have non-trivial homology, and then one has the Dehn twist which come from the ones which do have, which are trivial in homology. And so actually we arrived at this problem because we wanted to interpret in the case when the function was real analytic, this Grothendieck bilinear form takes values in R, and we don't only take multiplication by f, but we take multiplication by different powers of f, and we wanted to understand the signature of these bilinear forms. So this is, we arrived at this problem because we wanted to get a geometric meaning of these formulas. So we have the one for the topological one, and we have a conjecture about this.
Are there any questions?
If f is quasi-homogeneous, then n should be 0.
Excuse me?
If f is quasi-homogeneous,
N is 0.
then n is 0.
Exactly.
Do you see a new proof of this?
So if f is so this means that in this so if n is 0, then this means that there are no tubes of this form. So if f is quasi-homogeneous, then what happens is that if you have different components, then there is only one tube uniting the different. So for quasi-homogeneous, even for semi-quasi-homogeneous, n is 0. So in this case, there are no Dehn twists.